8. Storage management. To make the computer system convenient for users, the operating systems provides a uniform, logical view of information storage. The operating system abstracts from the physical properties of its storage devices to define a logical storage unit, the file. The operating system maps files onto physical media and accesses these files via the storage devices. Okay, the first part, file system management. File management is one of the most visible components of an operating system. Computers can store information on several different types of physical media: magnetic disk, optical disk, and magnetic tape are the most common. Each of these media has its own characteristics and physical organizations. Each medium is controlled by a device such as a device driver or tape drive that also has its own unique characteristics. A file is a collection of related information defined by its creator. Commonly, files represent programs and data. Data files may be numeric, alphabetic, alphanumeric, or binary. Files may be free-form, or they may be formatted rigidly. Clearly, the concept of a file is an extremely general one. The operating system implements the abstract concept of file by managing my storage medium, such as tapes and disks, and the devices that control them. In addition, files are normally organized into directories to make them easier to use. Finally, when multiple users have access to files, it may be desirable to control which user may access a file and how that user may access it. The operating system is responsible for the following activities in connection with the file management: creating and deleting files, creating and deleting directories to organize files, supporting primitives for manipulating files and directories, mapping files onto secondary storage, backing up files on stable storage medium. Section 2. Mass storage management. As we have already seen, because main memory is too small to accommodate all data and programs, and because the data that it holds are lost when power is lost, the computer system must provide secondary storage to back up main memory. Most modern computer systems use disks as the principal online storage medium for both programs and data. Most programs, including compilers, assemblers, word processors, editors, and formatters, are stored on a disk until loaded into memory. They then use the disk as both the source and the destination of their processing. The proper management of disk storage is of central importance to a computer system. The operating system is responsible for the following activities in connection with disk management: free space management, storage allocation, and disk scheduling. Caching. Caching is an important principle of computer systems. Information is normally kept in some storage system, such as main memory. As it is used, it is copied into a faster storage system, the cache, on a temporary basis. When we need a particular piece of information, we first check whether it is in the cache. If it is, we use the information directly from the cache. If it is not, we use the information from the source, putting a copy in the cache under the assumption that we will need it again soon. In addition, internal programmable registers, such as index registers, provide a high-speed cache for main memory. The programmer implements the register allocation and register replacement algorithm to decide which information to keep in registers and which to keep in main memory. Other caches are implemented totally in hardware. For instance, most systems have an instruction cache to hold the instructions expected to be executed next. Without this cache, the CPU Without this cache, the CPU would have to wait until several cycles while an instruction was fetched from main memory. Because cache have limited size, cache management is an important design problem. Careful selection of the cache size and of a replacement policy can result in greatly increased performance. Main memory can be viewed as a fast cache for secondary storage, since data in secondary storage must be copied into main memory for use, and the data must be in main memory before being moved to secondary storage for safekeeping. The file system data, which resides permanently on secondary storage, may appear on several levels in the storage hierarchy. Okay, like this picture. So you can see the information A is copied from magnetic disks into main memory, then from main memory to cache, then from cache to hardware register, okay? From disk to register. So the movement of information between levels of storage hierarchy may be either explicit or implicit, depending on the hardware design and the controlling operating system hardware. In a hierarchical storage structure, the same data may appear in different levels of the storage system. So, like this picture, the copy of A appears in several places: on the magnetic disk, in main memory, in the cache, and in an internal registers. Once the increment takes place in the internal registers, the value of A differs in the various storage systems. The value of A becomes the same only after the new value of A is written from the internal registers back to the magnetic disk. In a computing environment where only one process executes at a time, this arrangement poses no difficulties, since an assigned to integer A will always be to the copy at the highest level of the hierarchy. However, in a multitasking environment where the CPU is switched back and forth among various processes, extreme care must be taken to ensure that if several processes wish to access A, then each of these processes will obtain the most recently updated most recently updated value of A. The situation becomes more complicated in a multiprocessor environment, while in addition to maintaining internal registers, each of the CPUs also contains a local cache. In such an environment, a copy of A may exist simultaneously in several caches. Since the various CPUs can all execute in parallel, we must make sure that an update to the value of A in one cache is immediately reflected in all of other caches where A resides. This situation is called cache coherence, and it is usually a hardware issue. In a distributed environment, the situation becomes even more complex. In this environment, several copies of the same file can be kept on different computers, since the various replicas may be accessed and updated concurrently. Some distributed systems ensure that when a replica is updated in one place, all other replicas are brought up to date as soon as possible. I/O systems. One purpose of operating system is to hide the peculiarities of specific hardware devices from the users. For example, in Unix, the peculiarities of I/O devices are hidden from the bulk of the operating system itself by the I/O subsystem. The I/O subsystem consists of several components. A memory management component that includes buffering, caching, and spooling, a general device driver interface, drivers for specific hardware devices. Only the device driver knows the peculiarities of the specific device to which it is assigned.